explain the construction of solutions using eigenvalues of matrices. And then I will discuss a classical theorem of Bezout, which talks about intersections of plane algebraic curves. Okay, if you take two curves in the plane defined by polynomial equations, very often they intersect only in finitely many points, and we want to predict the number of solutions of f equal to 0 and g equal to 0 if f and g are polynomials which define the plane curves. I will indicate, mostly without proof, another approach to counting solutions using convex geometry. This method goes back to Newton. So it will be mostly without proofs. And one basic reference for what I have been discussing is a book of David Cox, John Little, and D. Oshia. It's a very interesting book. It is called Using Algebraic Geometry. So this book explains classical topics in algebraic geometry with applications and computational aspects. It emphasizes applications and computations. It is a highly readable book. So I advise you to look at the topics that I have covered in these 3 lectures in this book first. And there are many interesting exercises. Okay. Yeah, so let us begin. So we now know an upper bound on number of solutions. Okay, so this is the setup. We are considering polynomials in n variables with complex coefficients. I have a system of polynomial equations, f1 equal to 0, f2 equal to 0, and fs equal to 0. And so we know that star has a solution in Cn if and only if the ideal generated by these polynomials, okay, this ideal generated by these polynomials is not the whole ring. And when this is the case, the number of solutions, so remember V of I is set of all solutions. Okay. When this is the case, the number of solutions, we have seen it is less equal to the vector space dimension of R mod I. And equality holds if and only if I is a radical ideal. So we have an upper bound on the number of solutions. The question is, how do we construct solutions? So for that, we exploit the fact that R mod I is a vector space. It's a finite dimensional vector space. How to construct solutions? Yeah. So this is the main thing we want to get to. Yeah. So for this, we use the fact that our ring R mod I R mod I is a finite dimensional vector space. So I'm assuming that there are finitely many solutions. It is finite dimensional complex vector space. Okay, so suppose let D be the dimension as a complex vector space. Okay. Now we have in R mod I, on R mod I can define multiplication map by Xi. So this maps, this is a linear transformation. It takes a residue class in R mod I to residue class of XIF. And this MX1, MX2, and MXN are all linear transformations. Okay, these are linear transformations. So we can find a basis. So find a basis of R mod I, and then find the matrices for these linear transformations, MX1, MXN. So we'll have D by D matrices with complex entries. Okay, these are D by D matrices with complex entries. And these matrices, they commute with each other. Okay, this is an important observation. These linear transformations, MXI composed with MXJ is same as MXJ composed with MXI. Just calculate the left-hand side. MXI composed with MXJ acting on a residue class of a polynomial is equal to the residue class of Xi, Xj, F. But this is same as Xj, Xi, F. And this is equal to MXJ composed with MXI acting on F. So these are commuting matrices. Okay, and we have seen they're all diagonalizable. We have seen that. Okay, for all G in R. Okay, this linear transformation from R mod I to R mod I, and here I am replacing I by its radical. When you do that, the number of the solutions don't change. If I replace I by radical of I, the zero set of I and zero set of radical of I, they are one and the same. So when I is its own radical, then we have seen yesterday that this map MG is a diagonalizable map. It's a diagonalizable map. Okay. Do you recall what are the eigenvectors? Diagonalization means there should be a basis of eigenvectors. Does anybody recall what are the linearly independent eigenvectors for MG? Anybody?
The Lagrange polynomials actually corresponding to.
Yeah, can you be a little bit more precise?
That's polynomial with the G1, G2, and Gn, and they are actually the given point actually, they are given already previously point set actually Pi, that is finite set.
Yeah.
So suppose P1, P2, Pm, there are finite set of points. You can construct actually G1, G2, Gm, which is actually delta I actually. It takes Pj to delta.
Good. Good. So list the points. The dimension is D, and I'm assuming I is radical. So there are D.
That will be D. Yes.
There are D solutions. Okay, there are D solutions, and then find out the Lagrange interpolation polynomial. There are D of them. These are Lagrange polynomials. So we have seen yesterday in the tutorial that these polynomials exist. Okay, these polynomials exist, and then I proved yesterday that if you take the residue classes of the Lagrange polynomials belonging to our vector space, then mg operating on any of these vectors. Okay, do you recall what is the eigenvalue?
G of Pi actually for all possible. That G of Pj.
G of Pj. Okay, this is very important. Yeah, this is very important observation that any mg is diagonalizable, and the Gj's are linearly independent eigenvectors. So these are linearly independent eigenvectors. So in particular, therefore, when I take mx1, mx2, and mxn, these are commuting diagonalizable operators on my D-dimensional vector space. This is a complex vector space, and I have commuting diagonalizable operators. Do you know anything about the eigenvectors and eigenvalues of commuting operators from your linear algebra course?
Yes, I meant to say that.
Who is talking? There is some echo. What is the problem? Are two persons talking, or can you speak again?
Yes, sir. Hello.
Yeah. So they have common eigenvector, right?
Yes. Yes.
Commuting operators which are diagonalizable, they have common eigenvector. Is diagonalizability necessary over a complex vector space? Any operator has an eigenvalue and eigenvector?
Yes. Complex vector space, it is always diagonalizable.
Right. Well, no, it may not be diagonalizable. An operator may not be diagonalizable. Diagonalizability needs conditions, right?
Yes, yes.
Yeah. But we have proved that these are diagonalizable. Lagrange interpolation polynomials give eigenvectors, linearly independent eigenvectors. So they're all diagonalizable. Fine. But because they commute, there is a common eigenvector. Yeah. So because of this commuting property, there exists a common eigenvector. Hence, there exists an H in R such that when you take the residue class, this is a common eigenvector. Yeah, for all these linear transformations, mx1, mx2, mxn. So therefore, mxi operating on this common eigenvector, yeah. What did we prove in the first eigenvector theorem? When I operate mg on an eigenvector, what is the eigenvalue?
Eigenvalues are G of Pj actually. They are actually G is actually X actually.
You see, Vi is equal to P1, P2, Pd. Okay. And when I take a linear transformation mg, then its eigenvalues, the set of eigenvalues is called spectrum. So the spectrum, remember what was the spectrum? G of
X. G of P1, P2.
Yeah, you have to take the values of G on the set of zeros. So therefore, this mxi G, yeah, G is eigenvector. So that comes out. And the eigenvalue is this is the G. Xi as a function, what does it do on a point?
It's actually coordinate function actually equals to ith coordinate of that.
Yeah. So it will give me coordinate of some point, ith coordinate of some point.
Yes.
Right?
Yes.
So it will, you have to calculate this function on some point. Some point. We don't know which point it is, right? Okay. So we need a more precise argument, and this is called the theorem of Stickelberger. Stickelberger's theorem. So Stickelberger's theorem says that the zero set consists of these points A1, A2, AN in Cn, so that mxi, there exists a common eigenvector, so that mxi operating on this common eigenvector is equal to ai times common eigenvector for I equal to 1, 2, up to n. Every point, every solution of the original system of polynomial equation that we started with, if that system has finitely many solutions and I is the radical ideal, okay, this I'm assuming right now, although there is a more general version which doesn't assume that. So the set of common solutions is precisely given by using these operators, mxi. So mx1, mx2, mxn, they are commuting operators on a finite dimensional complex vector space. They have lots of common eigenvectors. So pick a common eigenvector and then take the eigenvalues for all mxi's, and then collect the eigenvalues and make this point. These are precisely all the solutions. So the problem of computing solutions of a system of polynomial equations is, by Stickelberger's theorem, is reduced to computing common eigenvectors of these. We know they exist, right? We know the common eigenvectors do exist. because they are commuting, they are diagonalizable operators. So common eigenvector exists. So you find more and more common eigenvectors. You will find more and more common solutions of the system of polynomial equations. And we know that there cannot be more than D solutions. We know an upper bound, so we know where to stop. So there are algorithms which does that. The only catch is to calculate these eigenvalues, we have to rely on approximation algorithm. There is no algorithm which produces exact eigenvalue. So we can only do an approximation of common solutions of system of polynomial equations. But this theorem reduces a non-linear problem. Computing solutions of a system of polynomial equations is a highly non-linear problem. There is no algorithm which produces exact solutions. We have to be happy with approximate solutions. But this theorem reduces it to a problem in linear algebra. Yeah, a non-linear problem has been converted into a problem in linear algebra for computing common eigenvectors. Okay, there are programs which you find these matrices. I find a basis of R mod I. Okay, there are algorithms, symbolic algorithms, which compute the basis of R mod I, consisting of monomials. Okay, using techniques from Grosvenor basis theory in commutative algebra, there are algorithms to compute the basis of R mod I. Once I have a basis of R mod I can calculate explicit D by D complex matrices which represent these n linear operators. So we can first construct these matrices. Once I have these matrices, there are very efficient algorithms to compute common eigenvectors. Okay. Once I get hold of a common eigenvector, then I will find the eigenvalues of mxi's, and these eigenvalues will give me one point in the solution space. And keep doing this. And we know there cannot be more than D points. Some of these points may occur with multiplicity. If your ideal is not a radical ideal, some solutions will occur with multiplicity, and one can calculate that multiplicity algebraically also. Okay, once I know the solution, one can calculate the multiplicity, how often it appears. All right, so this is an interesting result. Let us try to prove this. Any questions so far? Okay, so let us prove this. Yeah. All right. So VI, we know that VI, the set of solution consists of D points, where D is the dimension of R mod I. It can be less than D points if I is not a radical ideal. Yeah, this we do understand that. We understood this last time. So, but I'm assuming I is a radical ideal and D is the dimension, then there are D solutions. So suppose that the first solution is having coordinates A1, A2, and AN. Yeah. Then I know a basis of eigenvectors. So G1, G2, GD, these are interpolation polynomials, Lagrange interpolation polynomials for these points. And we know that these are common eigenvectors. These are eigenvectors of any multiplication operator, MG. So in particular, they are all eigenvectors of MX1, MX2, MXN also. Okay. So these are interpolation. So let's just verify, right? So look at look at xi g1 minus ai g1. Yeah, my point is this. I want to show that the coordinates of this point are eigenvalues. Okay. I want to show that coordinates of these points are eigenvalues of mx1, mx2, mxn, right? So take xi g1 minus ai g1 and calculate this at this point p1. Yeah, so this is xi g1 computed at p1 minus ai g1 computed at p1. Yeah. So can you tell me what it is? I mean, what is it? This is xi operating
of 1
and G1 operating on P1 minus AI G1 operating on P1 is 1. So this is just and xi of P1 is the ith coordinate of P1, which is AI, and this is 0. So this polynomial vanishes at the point P1. Similarly, I can show this also vanishes, okay, at Pj for every other, for all j. Same thing, because gi pj, g1 pj when j is not equal to 1 is 0. So this is clearly satisfied. So that says that this polynomial xi g1 minus ai g1, okay, it vanishes at every point, for all points in the variety of I. Okay, so therefore this polynomial belongs to the ideal of variety of I. But I is a radical ideal, so it is equal to I. So this polynomial belongs to I. That means the residue class are same. In R mod I. But the left-hand side is mxi operating on G1. The right-hand side is AI operating on G1. This is true for all I. Okay. Yeah, so every common solution is the coordinates of common solution are eigenvalues of mx1, mx2, mxn. Now let us prove the converse. Conversely, suppose I have a common eigenvector. I have a common eigenvector and eigenvalues are, say, bi for some non-zero eigenvector, and bi's are complex numbers. Then we want to show that b1, b2, bn is a common solution. Okay. Yeah. So that means we would like to show, this is same as showing that f b1, b2, bn is 0 for every f in this ideal. Every polynomial in this ideal vanishes at this point to prove that it is in the variety of I. Okay. But look at these commuting matrices, mx1, mx2, and mxn. These are n matrices, and this polynomial f is also a multivariate polynomial in n variables. So instead of the variables, I substitute these matrices. Yeah, remember, if I have a polynomial in one variable, I can substitute a matrix in that, right? And I get a matrix polynomial. Now I have multivariate polynomial. And these n linear operators, they are commuting with each other. So when I substitute mx1 for x1, mx2 for x2, etc., in this polynomial, I get a matrix polynomial in these n matrices. Okay, so this is a matrix polynomial. So for example, suppose I took f equal to x1 square x2 minus x3. Then, and so I suppose n was 3. Then what is mx1, mx2, mx3? That is mx1 square mx2 minus mx3. So this is a matrix polynomial because they are commuting. You see, mxi's are all commuting. And so I can just substitute as if these mxi's are indeterminate. So this is a matrix polynomial. Okay, this is a matrix polynomial. So you see, what we have is there is a common eigenvector of all the mxi's. Yeah. So if I operate this matrix polynomial on the same eigenvector, what happens? What happens? Take one variable case, no? One variable case. Suppose I have a matrix. If A is a matrix, and AV equal to lambda V. Now I take a polynomial in A. Say an plus an minus 1 plus a0 I. Okay, yeah. Then when I operate this FA on V, what do I get? What do I get?
F lambda 3.
F lambda
Times
V. Okay. So you must have done this exercise that eigenvalues of FA are F lambdas. Right? If I know eigenvalues of A, then eigenvalues of FA are F lambdas with same eigenvector. Same thing is true here. I know mx eigenvectors of mxi's. G is the common eigenvector of all the mxi's. The eigenvalues could be different. But this just like this, you do this calculation for this, and it will be F A1, A2, A3 times the same eigenvector. Okay. But you see the residue class of F is 0. Since F belongs to I. So that says that f of a1, a2, an, this is also 0. Read everything in R mod I. You see, we are operating on a residue class of a polynomial in R mod I, that's the eigenvector, but the residue class of f is 0 in R mod I. Okay, so when I take residue classes everywhere in this equation, I should get 0, but this is not 0. This is eigenvector, and therefore this value must be 0. So that is the proof. Okay, so that's the interesting theorem of Stickelberger, and you see we have made use of null Schönsatzs everywhere. Yeah, finite dimensionality of R mod I, when it is finite dimensional, if and only if there are finitely many solutions. And we use some facts from linear algebra that commuting operators have common eigenvectors. Okay. Yeah. So any doubts before I move to the next topic? Any doubts?
Hello, sir.
Yes.
I have one doubt. Not that Stickelberger theorem, in strong Hilbert-Knudsen, we have proved that there is a connection between algebraic varieties and radical idea.
Yes.
Is it possible to find some connection between, if we take any subset of Cn, it is possible to find some ideal which is in the solution set?
Yeah. If it is a finite set, yes.
It is possible. It is finite set, it is possible. But if we take any subset, arbitrary possible subset, I choose.
Not possible. Yesterday in the tutorial, it was proved. Suppose I take the lattice points where
yes,
integers.
That's the one example. Yes.
Yeah.
That's clear.
So not every subset is an algebraic variety.
Yeah, that's now it's clear. Thank you.
Right. Okay, any other question?
Could you go to the last part again?
Stickelberger theorem?
Yes, sir, the last.
Yeah.
Sir, I did not understand how this.
So do you understand the one variable? Yeah. Do you understand the one variable case?
Junaid, you want the question half minute?
Munir Nabi should mute himself.
Serious. Uniform conversion to point-wise conversion. Why not try?
Yeah. So do you understand the one variable case?
Yes, sir.
In the one variable case, when I take a matrix polynomial and operate on the same eigenvector, I get f lambda.
Yes.
Okay. So if this fa is 0, suppose matrix polynomial can be 0, right? If you substitute your matrix in the characteristic polynomial, you get 0 polynomial.
Yes.
Right? You get 0 matrix, right? Yeah. So there are some polynomials. When you substitute the matrix, you get the 0 matrix. Okay. So when fa is 0, but the right hand side, you see, right hand side is f lambda times v, and v is a non-zero vector. So that will force f lambda to be 0, right?
Yes.
Yeah. So that is what is happening. That my f is taken from the ideal. So its residue class is 0 in R mod I. Okay. So that is why.
Okay, sir, good.
Yeah. So this is 0 matrix. This f mx1, mx2, mx3 is 0 matrix. Because f belongs to I. Its residue class is 0 in R mod I. So this is 0 matrix, and so 0 operator, And but the right hand side is not is consisting of a multiple of a eigenvector. Eigenvector is non-zero entry in R mod I in this vector space. So F will vanish at these AIs.
Yes.
Okay, any other question? All right. So now I want to take the last topic, which is only an introduction. And I hope that you will feel interested in reading more about this. So this is about a classical theorem of Bezout, which takes two curves given by these equations. Okay. So F and G are polynomials with complex coefficients in two variables only. And I have two equations in two variables. So if you plot these two curves, yeah, you normally expect finitely many solutions. So if these have finitely many solutions, then the number of solutions is less equal to degree of F times degree of G. You see, we proved that if there are finitely many solutions, then we take Cxy over the ideal generated by F and G, and we showed that its dimension is an upper bound. Number of solutions is bounded by this, but this is more precise. Bezout's theorem is more precise. It is saying that this dimension is bounded above by product of the degrees. Once you know what F and G are, we know what their degrees are. So we don't have to calculate the dimension of this vector space, which can be very costly affair by symbolic methods. But it says the product of the degrees is an upper bound. Okay, in some small examples, you know why this is working. Suppose I have a parabola x square equal to y, and I take lines. If I take a line, okay, it is given by a linear equation. Linear equation has degree 1, parabola has degree 2, the product of the degree is 2, and there are in general 2 intersection points. There can be one intersection point, right? This x-axis is intersecting with only one intersection point. So the multiplicity should be assigned as 2 for that intersection point. So if you have a method to associate intersection multiplicity, which can be done, then Bezout's theorem simply says that the sum of intersection multiplicities at the common solutions is the product of the degrees. Yeah. If I know points in the variety of F and G, and I add up the intersection multiplicity at those points, it is the product of the degrees. I will not go into this precise statement. I will only explain the upper bound. Okay, so this is the classical theorem of Bezout. Okay, it is quite old, right? So I want to tell you a little bit about history here. Yeah. So first of all, Bezout's theorem, the fundamental theorem of algebra, which is due to Gauss. This came out in 1799. 1799. But Bezout's theorem is even older. Okay, but this is a misnomer because Newton already proved Bezout's theorem. Isaac Newton already proved Bezout's theorem in 1687. Okay, so there is a great work of Newton. Does anybody know the most famous book which Newton wrote? Hello? Does anybody know the most famous book which Newton wrote? Yeah, besides studying mathematics, you should also learn history, some important episodes in history of science and history of mathematics. Yeah, nobody knows what books.
Principles of Maths.
Yeah.
Principles of Maths.
Principia Mathematica. Okay, so let's say in those days, the language of science was Latin, and his book Principia. So this is the year of publication. So he wrote this book at the request of his friends. Yeah. So his friends started telling him that this person has found this theorem and that person has found this theorem. And then Newton was a perfectionist and he understood that other people are publishing what he already knew. So then he put many of his discoveries into this single book called Principia Mathematica. It's one of the greatest books written in science. And in the first book, there are many books in this, many chapters in this. So in chapter 1, lemma, he calls it lemma 28. Lemma 28 is Bezout's theorem. Principia Mathematica is freely available on the internet in English translation as well as Latin. And check it out. Lemma 28 is actually Bezout's theorem. So much before Bezout, Newton proved this theorem of about intersection of curves. And why was he interested in finding intersections? But Newton was interested in planetary orbits. So if you take planetary orbits, they are elliptic. Okay, they are all elliptic orbits. And he wanted to know whether planets will actually collide sometime. So you need to know intersections, but these are curves in three-dimensional space. So curves in three-dimensional space very often are given by two parametric equations, and he had to understand whether they will intersect any time. So he is working in four-dimensional space-time. Yeah, whether two planets will coincide in future. Yeah, they will collide in future. So he set up very complicated equations, but he has to first understand if you are given polynomial equations in four variables, whether there are common intersection points. So that's why he was interested. And his approach was extremely interesting. So what he does, he associates a polytope to a polynomial. Yeah. So suppose I have I'll first explain in terms of a bivariate polynomial. So suppose I have a polynomial in two variables. So a1 x u1 y u2 okay u1 v1 maybe u1 v1 plus a complex number x u2 y v2 and so on. And suppose I have n monomials x un y vn. Okay. So now what you do, you plot these exponent vectors. So u1 V1. Yeah. And then U2, V2. Maybe U3, V3 is here. They're all non-negative. So some of them could lie on x-axis and y-axis, and some are here. Okay. Now, if you have these finitely many points, you find the smallest convex set. So take the convex hull of these points, U1, V1, plot them in R2, UN, Vn. Yeah. So this is smallest convex set. Convex set is the set, smallest set, so that whenever I take 2 points, then the line segment joining them is in the set itself. Okay. So that is the convex hull. And one can algebraically define this as summation Ri. Suppose these points, these are points P2, this is P1, this is P3. So summation Ri Pi, where summation Ri is 1 and Ri's are non-negative real numbers. So algebraically also one can write down the convex hull, but this is a polygon in the plane. So this is called Newton polygon. Newton polygon of this bivariate polynomial. And you see, it completely ignores the coefficients. They are just non-zero coefficients, A1, A2, AN. So these monomials are distinct monomials, and take these n points and find the convex hull of these n points. That's called the Newton polygon. Okay, so suppose I have a polynomial gxy, which is a1 plus a2 x, a3 xy plus a4 y, and f, or another polynomial h, equal to b1 plus b2 x square y plus b3 xy square. Yeah, then we can plot the Newton polygon. Yeah, this is a monomial which is constant monomial 1. So that has coordinate 0, 0. So this monomial is constant monomial, which is 1, and so its exponent vector is 0, 0. So I label it as A1. Then A2, that's the coefficient with this monomial x. So the exponent vector is 1, 0. So that goes with A2, 1, 0. Okay. And then A3 goes with xy. The coordinates are 1, 1. So I label this as A3. These are just labels. Then A4y is here. So these are the 4 points. Then I take their convex hull. So convex hull is this square, solid square. So that is the Newton polygon of G. Then I can write down the Newton polygon of H. So B1 will be the origin, and this is x square y. So here is my x square y. Okay, that is I label it as B2. Then B3 xy square. So xy square is somewhere here. Okay, so then take the convex hull. So that is the Newton polygon of H. So every polynomial has its associated Newton polytope. So suppose I take a Laurent polynomial in many variables. So Laurent polynomial is a linear combination of monomials. Okay, this x alpha is a monomial, x1 alpha 1, x2 alpha 2, xn alpha n, where alpha 1, alpha n are integers. I am not saying that they are non-negative. They could be any integers. Then this is what is called a Laurent polynomial. And suppose I display the monomials where coefficients are non-zero. Yeah. Then each monomial will give rise to a lattice point, alpha 1, alpha 2, alpha n. So take those lattice points and plot them in the n-dimensional Euclidean space. Okay. So locate the lattice points alpha equal to alpha 1, alpha 2, alpha n in Zn, so that a alpha is not equal to 0 in my Laurent polynomial. And then take the convex hull, and that is called the Newton polytope of this Laurent polynomial. Newton polytope of f, and this is the convex hull of all the alphas such that a alpha is not equal to 0. So this is a closed bounded set in Rn. Yeah. So every Laurent polynomial has a associated Newton polytope in n-dimensional Euclidean space. If I'm dealing with bivariate polynomials, I get Newton, the polygons, convex polygons. Okay. Yeah. So now I want to define a quantity called Minkowski's sum. Minkowski's sum of polytopes. So suppose P and Q are polytopes. So polytope is a convex polytope is a convex hull of finitely many points in Rn. Okay, that's the general definition. Convex polytope, you take finitely many points in Rn. They may not be lattice points. Any finitely many points in Rn, then take the convex hull of those points. That is called a convex polytope. So I take any two convex polytopes in a n-dimensional space, Euclidean space. Then their Minkowski's sum is simply you add the points where U is in P and V is in Q. Yeah. So suppose I take a line segment. Okay, this is my line segment. This is a convex set. Yeah. Then I take another line segment. This is a convex set inside R2. I'm thinking of this as a convex set in R2, and take another convex set here in R2, this line segment along y-axis. What is the Minkowski's sum? Can you tell me what the Minkowski's sum? Stretch your imagination. Tell me the Minkowski's sum of these two unit line segment, one on x-axis, another on y-axis, as polytopes in the two-dimensional plane. So you should be able to answer this. Anybody? What is the Minkowski's sum?
It is the triangle joining two vertices L1 and L2.
Triangle. So the Minkowski's sum.
Rectangle, says rectangle.
Square or rectangle?
Is it unit square? It is
unit square. Yeah. It is not triangle, it is the unit square.
Yes, sir.
Because you see, 1, 0, and 0, 1, both are, I mean, 0, 1 is in L1 and 1, 0 is in L2, and I can add them, you see, I get 1, 1. And that is the farthest point you can get. And so if you pick some point from here and some point from here, I will get this point. So all the points of this square are covered. So Minkowski's sum, the line segment is a one-dimensional polytope, but the Minkowski sum turned out to be two-dimensional. Yeah. Okay. But it is a polytope. So this is a theorem which I am not proving. Minkowski sum of finitely many polytopes is a, convex polytope is a convex polytope. Take some proof. Yeah. So basic books on convex geometry, they prove this thing. Okay. So now I define, suppose let P and Q, okay, they are in R2. These are convex polytopes, convex polygons. Because they are in R2, they are convex polygon, or they can be line segments. Yeah. So these are convex polytopes in R2. Then I define what is called the mixed area. Mixed area of P and Q. This I denote by MPQ. This is a quantity which is area of the Minkowski sum minus area of P minus area of Q. Okay, so I must define what is volume in order for this to make sense. Volume of a polytope in Rn. Okay, so first of all, if dimension of a polytope is less than n, so take say line segment in the plane. Okay, its area will be declared to be 0. But you have a polygonal region like a square or a rectangle, or then they will have an area. So if dimension of the convex polytope is smaller than the dimension in which the polytope lives, then we will say its volume is 0. Okay. Otherwise, that is, if dimension of P is n, then volume of P is given by a multiple integral. Over the polytope. Polytope is a compact set. Yeah, it has its volume, and the function 1 is integrable on P. Okay, P is very nice, and its volume is this multiple integral. Okay, so in that sense we have to take this area of P plus Q minus area P minus Q. So if P and Q were those two line segments, one along the x-axis, another along the y-axis, then the area of P is 0 and area of Q is 0, but area of P plus Q is 1. Yeah. So that's the mixed area of those two unit segments, one on x-axis, another on y-axis. Right? But let me take two triangles. Suppose this is my triangle P. Okay. And this is side A. This is also side A. And I take another triangle. This is convex set, this side B and this side B. Okay. So when I add these, what happens? This will be a triangle. Side is A plus B. The Minkowski sum is a triangle with side A plus B. Okay. So what is the mixed area? Suppose this is my P and this is Q. This is P plus Q. The mixed area of P and Q is area of P plus Q minus area of P minus area of Q. So area of P plus Q is A plus B square over 2 minus A square over 2 minus B square over 2. What is it? What is this number?
AB.
AB. Okay. So that is why it is called mixed. The dimensions of these two triangles, they are getting multiplied and we get the mixed area. Okay. So now let me state. So in the around 1975, okay, a Russian mathematician named D. Bernstein he proved a fantastic result. It says that suppose let f xy and gxy be Laurent polynomials. So Laurent polynomials are polynomials in x and y and x inverse and y inverse. I take two Laurent polynomials. And when you take Laurent polynomials, because some variables can be in denominator, we can only talk about their zeros, okay, in C star. Okay, C star. C star is C minus 0. So let us take two Laurent polynomials, f and g, and suppose let f equal to 0 equal to g have finitely many solutions in C star square. Then the number of solutions is bounded above by mixed area of the Newton polygon of F and Newton polygon of G. And if F and G are generic means if you just take random polynomials, randomly selected polynomials, then equality is true. Okay, so you see the right-hand side quantity is a continuous quantity. Newton mixed area of two polygons involves the area of those polygons, right? So that's that, but it says that is an upper bound on number of solutions. Left-hand side is a discrete quantity, okay? And it doesn't pay any attention to the coefficients of the polynomials. But even then, it is able to predict the number of common solutions. Okay, so let us see that the classical theorem of Bézout is implied by Bernstein's theorem. Bernstein's theorem implies Bézout's theorem. And of course, a small exercise for you to prove that Bézout's theorem implies fundamental theorem of algebra. Okay. Yeah, so let us prove that. So suppose f These are two polynomials. F and G are two polynomials having finitely many common roots, having finitely many common solutions. Okay. And suppose the degree of F is D and degree of G is E. So when I write F as a sum of monomials, A alpha, X alpha 1, Y alpha 2, okay, and G as sum of B alpha, X alpha 1, Y alpha 2, okay, then this mod alpha is less equal to D. And here, mod alpha is less equal to E. So F may involve monomials of degree at most D, and G may involve monomials of degree at most E. So when I plot the Newton polygon of F, I look at monomials of degree at most D. Okay. So if I suppose this is a monomial of degree D, then alpha 1 plus alpha 2 is D, but alpha 1 plus alpha 2 equal to D, this lies on the line where this is D is 0 and this is 0D. So all monomials of degree D, they lie on this line. Okay. Monomials of degree D minus 1, they will lie on this line, etc. So when I plot the Newton polytope of F, yeah, it will be a subset of this triangle. The Newton, let us call this as P. Newton polygon of F is a subset of P. Similarly, when I plot the Newton polygon of G, this is degree E. So take this triangle where this has coordinate 0, E, and this has coordinate E0. So take this triangle, then Newton polygon of G is contained in this triangle. So the mixed area of Newton polygon of F and Newton polygon of G. Okay. Now one proves that if you replace polytopes by bigger polytopes, then the mixed area may increase. It cannot decrease. This is less than, I replace this Newton polygon by a bigger polytope. Then one proves this result in convex geometry that the mixed area of Newton polygon of F and Newton polygon of G is less equal to mixed area of P and Q. But we just found the mixed area of P and Q, where this was D times E. Yeah, so that's all. So this is the Bezout's theorem. This is the shortest proof of Bezout's theorem, assuming, of course, the result of Bernstein. Any questions? Right. So let me prove Bezout's theorem in a special, the Bernstein's theorem in a special case. Right. Yeah. First of all, there is a remark. Bernstein's theorem is sharper gives better bounds than Bezout's bound. Okay. So just take our G, which I introduced earlier, A plus BX plus CXY plus DY, and H equal to P plus Q X square Y plus R XY square. So Newton polygon of G is this square, and Newton polygon of H is this triangle. And their Minkowski sum, you can calculate Minkowski sum. Okay. It will be some polygon, but the mixed area of this P and Q will turn out to be, if you plot P plus Q, that is going to be a polygon, and its area you can find out. It's 13/2. Area of P is 1. Area of Q is 3/2. And this is 4. So it says that the number of intersections of G, the curves defined by G equal to 0 and H equal to 0, will not exceed 4. But you see, the degree of G is 2. Degree of G is 2, and degree of H is 3. So Bezo's bound says that there will be at most 6 points of intersection. But Bernstein's theorem says there will be at most 4 points of intersection. So it gives a better bound. Yeah. All right. So in the remaining time, let me prove Bernstein's theorem in a special case. So general proof you can read in this book by Cox Little using algebraic geometry, whose reference I gave. But let me prove this for a special case. Proof of Bernstein's theorem for binomials. A binomial is a polynomial which has 2 monomials. So take F1 equal to alpha XA YB. Okay, minus beta XC YD. Alpha and beta are complex numbers, and A, B, C, D are integers. Okay. Take F2 XY equal to gamma XEYF minus delta XGYH. Okay. Yeah. So Bernstein's theorem says look for common solutions. These are Laurent polynomials. Okay. Laurent binomials. So the exponent vectors can be negative. So we are looking for solutions. We are looking for solutions in C star square. Okay. Yeah. Now, when you multiply a Laurent polynomial by a monomial, how does it affect the Newton polygon? So there is a Newton polygon of F1, and then you multiply a monomial, say X, XR, YS with F1. What is the relation between these 2 polygons? Can anybody guess? How do I get Newton polygon of XR, YS, F1 from Newton polygon of F? Yeah. So exercise. Newton polygon of FG is the Minkowski sum of the individual Newton polygon. So Newton polygon of XR, YS, F1 is Minkowski sum of single monomial, Newton polygon of single monomial. That is just a point. So this is, suppose RS is this vector, then, and this Newton polygon of F is P, then this is just this. So this is equal to RS plus, okay. So it's a translate. Yeah. So if I multiply a Laurent polynomial by a monomial, then the Newton polygon just gets translated. Under translation, the volume doesn't change, and mixed volumes, mixed areas, they will not change. But the number of solutions will change. But number of solutions in C star square will not change. Because if you look for solutions in C star square, then X and Y will not be 0. So solutions of F1 and solutions of XR, YS, F1, they are same in C star square. Okay. So if I'm looking for solutions in C star square of F1 and F2, I can multiply F1 and F2 by any monomials without affecting the mixed area, without affecting the number of solutions. So therefore, I take a monomial whose exponent vector is high enough, high positive number, okay, and multiply that with F1 and F2, then I may assume, okay, I can assume that my binomials are of this type: XA, YB minus alpha, and the second binomial is XC, YD minus beta. Yeah. So the original F had two monomials. I can just multiply this F1 by X minus C, Y minus D. Okay. Then I will be left with a constant and then divide by the leading coefficient. It is not going to affect the number of zeros or the volume, because Newton polytope disregards the coefficients. So I can reduce the problem of computing the solutions of binomial equations to solutions of such binomials. Yeah. So that is why Bernstein's theorem is about zeros in C star. It is not a theorem about zeros in C square, because I'm modifying by polynomials by multiplying by monomials. If you multiply by monomial, number of zeros in C star doesn't change. Okay, but number of solutions in C square will certainly change. So I can assume that G1 and G2 are of this form. That is a good simplification. Okay, now let us make a matrix. So exponent vector is AB. Make a matrix where the first row is the exponent vector of XY, and the second exponent vector for in G2 is SCD. This is a 2 by 2 integer matrix. Okay, when I have 2 by 2 integer matrix, any square integer matrix has a form called Hermite normal form. If you have not studied, please study that. So there are various normal forms of matrices like Jordan form or Hermite normal form or Smith normal form. So if I have integer matrix, 2 by 2 integer matrix, it has a Hermite normal form, and the Hermite normal form is an upper triangular matrix with integer entries, and it can be obtained by row operations, okay, with integer entries. So there is a matrix, integer matrix with the determinant 1. So that is a statement of Hermite normal form, that I can pre-multiply by a integer matrix of determinant 1 to convert my given matrix to Hermite normal form. A21, A22. So there exists such a matrix so that this is true. All right. Yeah. So now we will use this Hermite normal form. So G1 equal to 0 equal to G2. We are looking for solutions of G1 and G2, but that is if and only if X A Y B equal to alpha and X C Y D equal to beta. Okay. So I'll combine these two equations and take XA, YB and raise it to U11. Okay, U11 is coming from this matrix. Okay, and then XC, YD, raise it to U12. So take the first row of this matrix and raise these two equations by U11 and U12, but that is equal to alpha U11, beta U12. I do the same thing and look at the second row of the U matrix, XA, YB, okay, to the power U21, XC, okay, XC, YD to the power U22, and that is alpha to the power U21, beta to the power U22. Okay, so you can see that G1 and G2 are 0 if these two are satisfied. But you see, now look at R. This first entry R is the dot product of this first row U11, U12 with the first column vector A and C. Okay. Yeah. So this is where I am multiplying. So I get A U11 and then plus C U12, but that is equal to R. And then B U11 and D U12, but that is equal to S. So I get XR YS equal to alpha U11, beta U12. And the second equation gives me Y to the T, okay, is equal to alpha U21, beta U22. So you see, these equations, G1 equal to G2 equal to 0, has been simplified to these two equations. Now this last equation involves only, X has disappeared. So I have reduced my original system of two binomial equations into a triangular system. The last equation is Yt equal to some complex number. So this last equation has T solutions, T distinct solutions. And so each one of those solutions in Y, if I substitute into the first equation, I will get R solutions. So therefore, there are RT solutions. Okay, RT non-zero complex roots, RT solutions in C star square. Okay, but you see, the matrix equation was U11, U12, U21, U22 times AB, CD is equal to RS 0T. But this determinant is 1. So I get this determinant of AB, CD is equal to RT. But determinant of ABCD, yeah, my G1 was XAYB minus alpha, and G2 was XCYD minus beta. So what is the Newton polygon of G1? Yeah, so this alpha goes with the constant term. So Newton polygon of G1. What is the Newton polygon of G1? So alpha, I get this point, and AB is this point. So this is the line segment. This is the Newton polygon of G1. And similarly, I will get Newton polygon of G2. I take this point CD. When I take the Minkowski sum, then what do I get? if I take these two inclined line segments, what is their Newton polygon?
A line segment joining origin and A plus C and B plus D.
It is not a line segment. We have seen when you took line segment along x-axis and along y-axis, we got a square, no?
Yes, yes.
So it will be a parallelogram. It will be a parallelogram like this. What is the area of this parallelogram? I know this. What is the area of parallelogram? Determinant of ABCD. But that determinant is RT. That determinant is RT. So mixed area of these two line segments. So Newton polygon of P G1, let's call this as P. Newton polygon of G2, let's call it as Q. That mixed area of P and Q will be area of P plus Q, which is this parallelogram, minus area P is 0, area Q is 0, because P and Q are line segments in R2, their areas are 0. So this is just the determinant of, so this is AD minus BC, but this determinant is RT. So we have derived Bernstein's theorem for binomials using the Hermite normal form of 2 by 2 integer matrices. Okay. So in this book of Cox-Locia, the general Bernstein's theorem is proved, okay, using methods of convex geometry. And this gives a new proof of Bézout's theorem for Laurent polynomials in n variables and Laurent polynomials in n variables. So if they have finitely many common zeros in C star to the power n, then the number of common zeros is bounded above by the product of the degrees of Laurent polynomials. This is the Bernstein's theorem for n variables, and a proof is given in this book using methods of convex geometry. I have just discussed a small flavor of this interesting result in the special case, okay, yeah, for binomials. All right, so our time is finished. There are many interesting topics about solutions of polynomial equations. The entire field of algebraic geometry discusses algebraic varieties,